Hello everyone, welcome to this video. We will talk about two very important concepts in deep learning, which is underfitting and overfitting. So in our example data, let's pretend that H is for healthy people and S is for sick people. So maybe all the healthy people live in the good part of town and all the sick people live in the bad part of town. Although interestingly, there's one healthy person in the bad part of town, which will be important to note later on in this video. So, an ideal fit would have a line that cleanly divides the healthy people from the sick people. But instead, the model draws a line like this, where roughly half the healthy people and half the sick people are on either side of this line. Our model will have terrible performance. We will have the same odds as flipping a coin, randomly between heads and tails. So in underfitting, the model learns poorly from the training data, the model is too simple, roughly the same chances or odds as flipping a coin. So how do we reduce underfitting? You can train longer on your existing training data. This would be the equivalent of telling a student to study more for their test, use more training data, check your data. So for example, does the data have useful features like favorite color? Maybe if our model was trying to see how likely someone will buy something, favorite color will be useful. But when it comes to determining if someone is healthy or sick, favorite color is not as useful. The model is too simple, so increase the model complexity. More layers, more perceptrons. What about overfitting? Now our model has a line that cleanly divides the healthy people from the sick people, but it tries to accommodate this one healthy person a bit too much and creates like this alleyway or corridor just to reach this one healthy person. So in overfitting, the model learns too much from the training data. The model is too complex. This one healthy person we see here in the corner could be an invalid measurement or a valid outlier. And the model performs well on the training data, but not on new data. Maybe in real life, everyone living in this weird alleyway or corridor should be S for sick, but our model will falsely believe everyone in this narrow alleyway or corridor is H for healthy. As we mentioned earlier on in this course, if your model has good results on the training data, it does not mean it will have good results on new data. So how can we reduce overfitting? Use more training data. The model is too complex. Reduce model complexity with regularization. And we will go over these three regularization things right here. So in early stopping, let's define the term epoch. It is a complete pass through the entire training data set. In case you're wondering what this epochs here means. So later in training accuracy increases and validation accuracy decreases. Remember earlier on in the course, we talked about how validation data serves as a proxy or estimation of new data. So at some point during training, your model will do good on training data, but not good on new data. So yes, in overfitting, the model learns too much from the training data. The model performs well on the training data, but not on new data. Once the model starts overfitting, stop training. So right here, the validation accuracy starts to decrease. We early stop right there. For L1 and L2 regularization, let's review this diagram from earlier on in the course again. Your model has weights, which is used to generate outputs like, I think this is a picture of a dog, or I think this is a picture of a cat. We use the error or loss, tell the model if its prediction is correct or incorrect, and then that error or loss is used to update the weights to hopefully have better weights for better predictions of it if it is a picture of a dog or a cat. So you can think of the weights as like the brain cells of the model or like the knowledge of the model. So in L1 and L2 regularization, both update the loss to penalize large weights. Large weights add complexity. In L1 regularization, weights of 0 possible, so you can exclude features like favorite color. In L2 regularization, weights of 0 not possible, include every feature, unimportant features minimized. We will not go over the math used in L1 or L2 regularization, but just remember these key points about weights of 0 possible and weights of 0 not possible. In dropout regularization, randomly deactivate neurons / perceptrons during training. So here is our neural network / model. Sometimes during training, this perceptron and this perceptron become dead. And sometimes during training, this perceptron and this perceptron become dead. And what this does is it stops a perceptron from becoming too specialized. Because when a perceptron becomes too specialized, it's more likely to overfit. Here is a chart summarizing everything we've talked about in this video. Feel free to pause and read over everything. But what I want you to focus on is this. Your model can be too simple or too complex. The end result is the same. Poor performance on new data. So we want our model to have the best results on new data to have just the right amount of complexity. And when your model is too simple, increase the model complexity. And when your model is too complex, reduce the model complexity. And here are some diagrams to summarize everything we have learned in this video so far. So in underfitting, the performance is terrible. We might as well flip a coin for heads and tails. For overfitting, the performance does get better, but because our model tries so hard to accommodate the training data with this healthy outlier or invalid measurement, it's going to falsely think everyone in this corridor is a healthy person when it should be a sick person, S for sick, and the ideal fit looks something more like this. Okay, thanks for watching this video.